In this video, we'll begin with the most critical failure in terms of operational impact, frequency, and repair costs within a photovoltaic plant: failures in IGBTs, insulated gate bipolar transistors, and power modules. These failures represent 34% of all incidents detected in the power converters integrated into inverters. This is not simply a technical failure. We're talking about an essential component whose failure can cause the inverter to completely shut down, directly affecting energy production and project revenue. Their significance is such that, in many cases, these events are considered critical incidents that trigger emergency protocols. IGBT failures represent 34% of the total failures detected in utility-scale photovoltaic inverters, making them the most common type of failure in real-world environments. The main causes can be accumulated thermal stress under high irradiance conditions or poor cooling. Intense power cycling due to rapid load variations. Premature aging of conductive materials and solder pastes. Electrical transients, voltage and current spikes, not properly mitigated. The most common types of failures are wire detachment due to cyclic thermal vibrations. Solder fatigue at the contact points of the package. Degradation of chip adhesion due to poor thermal design or overloading. Fault at the thermal interface between the chip and the heatsink, affecting heat dissipation. The breakdown by type of failure can be thermal, 45%. The main cause of failure and difficult to detect without specific sensors. Electrical, 35%. Associated with overloads, internal short circuits, or transients. Mechanical, 20%. Related to vibrations, structural fatigue, or poor assembly. MTTR, mean time to repair, between 4 and 8 hours if spare parts are available on site. This time can extend to several days or weeks if stock is not available, seriously impacting system availability. IGBT technology is extremely critical in inverters. It allows rapid switching between direct and alternating current and operates under highly demanding thermal and electrical conditions. Due to its complexity and sensitivity, this type of component cannot be replaced by non-specialized technical personnel. Specific training in power electronics is required. Some maintenance strategies should include availability of critical spare parts in key locations, strategic stock, continuous thermal monitoring using embedded sensors or advanced SCADA systems, scheduled inspections to check the integrity of welds, interfaces, and heat sinks. The most common symptoms prior to or associated with the failure are progressive drop in inverter efficiency. SCADA alarms activated without apparent cause. Total shutdown of the inverter system with no remote restart option. Each failure of this type results in an immediate shutdown of the affected inverter. If there is no redundancy or auxiliary inverters, the loss of generation can range from 1 to 5 megawatts per event. The replacement cost of an industrial IGBT module can be between €2,000 and €5,000 per unit, plus the cost of specialized labor, urgent travel, and possible contractual penalties for unavailability. In scenarios without available spare parts, losses can multiply exponentially. Critical hours of solar irradiation between 11 a.m. and 5 a.m. are lost, directly affecting the project's monthly profitability and accumulating an unrecoverable opportunity cost. To prevent these incidents, the following can be implemented: advanced thermal management, use of active cooling systems, forced ventilation, and high thermal conductivity materials. Thermal sensors distributed across the plate and contact points to detect anomalous heat buildup. Predictive monitoring based on artificial intelligence. Detection of thermal and electrical drift before failure occurs. Scheduled power reduction. Mitigation strategy in times of extreme risk, for example, prolonged heat waves, dirt buildup, severe weather events. The IGBT is the electronic heart of the solar inverter, and as such, if it fails, the entire system collapses. Preventing its failures is not just a technical advantage or an improvement in maintenance, it's a financial and operational obligation. Because an unforeseen failure can cost much more than a simple repair, it can jeopardize the overall profitability of the project, affect the fulfillment of a PPA, and damage the operator's image with the end customer. We now turn to one of the most common breakdowns in photovoltaic plants: failures in the inverter cooling systems. Although they often don't cause a complete shutdown, their cumulative impact on energy efficiency, component lifespan, and economic performance is considerable. In fact, this type of failure tops the list of incidents, yet it remains one of the easiest to prevent if managed properly. Fans often fail due to natural wear and tear, blockage by dust or dirt, or even electronic failures in the motor. Bearings also frequently deteriorate over time. Although the average repair time is low, between 1 and 3 hours if a replacement is available, the real problem arises when these failures coincide with periods of high irradiance, precisely when the plant could be producing at its maximum. At these times, the system enters thermal limitation mode or even shuts down, resulting in a direct loss of revenue and the risk of permanent damage to internal components such as IGBTs or capacitors. From an operational perspective, these failures result in automatic power reduction, triggered SCADA alarms, and, in extreme cases, shutdowns due to overtemperature. To detect them early, the most effective approach is a combination of continuous temperature monitoring, infrared thermography, and periodic visual inspections. SCADA alarms also help, but they are no substitute for a well-planned preventive inspection. From a financial perspective, the problem is even more significant. While repairs may not entail a significant cost, the loss of production during key hours, such as midday in the summer, represents a significant drop in revenue per MWH. Furthermore, failure to act quickly can lead to secondary damage that requires costly repairs. All of this makes this failure one of the most damaging silent leaks for a plant's profitability. That quote S why it's key to implement preventive measures. Regular cleaning of filters and grills, availability of spare parts on site, and if possible, incorporating cooling redundancy through an N+1 configuration. Planning monthly inspections with thermography and SCADA data can make the difference between a stable plant and one that steadily loses performance without anyone noticing. In short, this isn't the most expensive failure, but it is the most repetitive. And as is often the case in industrial operations, invisible and cumulative costs are those that most affect the bottom line. Therefore, thermal management must cease to be a secondary issue and become a priority in any well-structured O&M strategy. The third major category of inverter failures is capacitor failure. Although not the most common, their impact is very high and their danger should not be underestimated. A failure in these components can completely shut down the inverter, affect other critical system elements, and, in extreme cases, pose a fire risk. It is important to understand that capacitors, especially DC link capacitors and AC filters, are components with a limited lifespan that degrade cumulatively and silently. Therefore, by the time the failure is detected, it is often too late, and the technical and economic consequences are already underway. The most common failures are usually caused by excessive heat, overvoltages, or simply the natural aging of the component. Visible signs of degradation, such as casing swelling, electrolyte leaks, or thermal discoloration, help us identify the problem, but often these signs appear when the component is practically at its operating limit. Therefore, it is essential to monitor parameters such as capacitance and ESR to detect patterns of deterioration before complete failure occurs. When this happens, the inverter stops, and we need qualified technical personnel to perform a repair, which is not always simple. From an economic perspective, a failure of this type has several levels of impact. We are not only talking about the cost of the component, but also the energy not produced during the shutdown, the intervention time, and the potential damage to other components such as IGBTs or control boards. Furthermore, if the failure involves a catastrophic leak or explosion, the extent of the damage is multiplied, and repairs may require replacing multiple components and overhauling the entire system. This increases both direct and indirect costs, including penalties for unavailability or breach of PPA contracts. For all these reasons, prevention strategies must focus on maintaining a controlled thermal environment, conducting regular visual inspections, and, above all, implementing continuous monitoring of key electrical parameters. Data-driven preventive replacement is much more cost-effective than waiting for a failure to occur. Because, as we often say in the field, capacitors don't give warning. They degrade silently, and by the time they explode, it's already too late.